Fermat's Little Theorem is a fundamental theorem in number theory and has vast applications in mathematics and cryptography. A Swiss mathematician, Leonhard Euler, generalized Fermat's Little Theorem, which is now called Euler theorem in number theory. Later, the Euler theorem became the core of the RSA public key encryption. In this video, I'll explain Fermat's theorem with the help of small examples. I'll then show you an application of Fermat's theorem in finding remainder when an integer with a very high exponent is divided by a prime number. Fermat's little theorem has two variants. The first variant is applicable in the case of any prime number and any positive integer. The second variant applies when a is not divisible by p. The first variant says that if a is any integer and p is a prime number, then a raised to the power p is congruent to a modulo p. Let us briefly look at what is meant by a number is congruent to another number. The statement that b is congruent to a modulo n means b minus a is divisible by n. Please keep in mind that it will be incorrect to say that the remainder is a when b is divided by n. It only means b minus a is divisible by n. 38 is congruent to 10 modulo 7. 38 is also congruent to 17, 3 and minus 4 modulo 7. In fact, 38 is congruent to an infinite list of integers modulo 7. It does not mean that 10 or 17 is the remainder when 38 is divided by 7. The remainder is only the non-negative integer less than 7. In this case, the remainder is 3 when 38 is divided by 7. So the statement that a raised to the power p is congruent to a modulo p means a raised to the power p minus a is divisible by p. The second variant says that if a is not divisible by p, then a raised to the power p minus 1 is congruent to 1 modulo p. It means that a raised to the power p minus 1 whole minus 1 is divisible by p. It is important to note that the converse of the Fermat's theorem is not true. These equations can also hold for composite integers instead of a prime number p. But if p is a prime, these equations will always hold. Let us look at some examples. A is equal to 3 and p is equal to 5. A is not divisible by p, so we verify both variants using this example. A raised to the power p is equal to 3 raised to the power 5, which is equal to 243, and 243 is congruent to 3 modulo 5. So a raised to the power p is congruent to a modulo p. In case of the second variant, a raised to the power p minus 1 is equal to 3 raised to the power 4, which is equal to 81, and 81 is congruent to 1 modulo 5. The second variant remains true as well. In this example, both a and p are equal to 3. A is divisible by p in this example, so the second variant of the Fermat's theorem will not hold. Nonetheless, we will try to use the second variant as well to see what happens. The first variant, a raised to the power p is equal to 3 raised to the power 3, which is equal to 27, and 27 is congruent to 0 modulo 3. Don't worry, 27 is also congruent to 3 modulo 3. The first variant is true. Let us try the second variant, although it does not apply to this example. A raised to the power p minus 1 is equal to 3 raised to the power 2, which is equal to 9. 9 is congruent to 0 modulo 3. Is 9 congruent to 1 modulo 3 as well? The answer is no. 9 is congruent to 0, 3, 6, 9 and all multiples of 3, but it is not congruent to 1 modulo 3. You see, the second variant does not hold for this example. It only holds when a is not divisible by p. Our next example has a equal to 10 and p equal to 3. Let us verify the theorem. A raised to the power p is equal to 10 raised to the power 3, which is equal to 1000, and 1000 is congruent to 1 modulo 3. But 1000 should be congruent to 10 modulo 3. And in fact, it is congruent to 10 modulo 3 because 1 is congruent to 1 plus any multiple of 3. So the statement a raised to the power p is congruent to a is true. Since a is not divisible by p, the second variant is also applicable. a raised to the power p minus 1 is equal to 10 raised to the power 2, which is equal to 100, and 100 is congruent to 1 modulo 3. The second variant also holds. We have seen three examples. In the first example, p was greater than a. In the second example, we chose p equal to a. And in the third example, a was greater than p but not divisible by p. In this example, we have chosen a greater than p and also divisible by p. Let us try Fermat's theorem on this example. A raised to the power p is equal to 12 squared, which is equal to 144, and 144 is congruent to 0 as well as congruent to all multiples of 2. Therefore, 144 is also congruent to 12 modulo 2. The first variant of Fermat's theorem always remains true regardless of whether a is greater than or less than p, or a is or is not divisible by p. Let us try the second variant. A raised to the power p minus 1 is equal to 12, and 12 is congruent to 0 modulo 2. This means that 12 is congruent to 0 plus all multiples of 2. 12 is congruent to 0, 2, 4, 8, and so on, as well as congruent to minus 2, minus 4, minus 6, and so on. But 12 is not congruent to 1 modulo 2. The statement no longer remains true because 12 is divisible by 2, and this variant of the Fermat's theorem is not applicable. Let us look at one application of Fermat's theorem in finding the remainder when a number with a very high exponent is divided by a prime number. I'll find the remainder using Fermat's theorem when 7 raised to the power 567 is divided by 13. We have already seen the Fermat's theorem. It is a raised to the power p minus 1 is congruent to 1 modulo p. Since 13 is not divisible by 7, substituting 13 for p and 7 for a, we have 7 raised to the power 12 congruent to 1 modulo 13. Using the division theorem, we can write 567 as 47 times 12 plus 3. We have not chosen these numbers randomly, but we calculated remainder 3 when 567 is divided by 12 and wrote 567 equal to the remainder 3 plus 12 times 47. So we can write 7 raised to the power 567 as 7 raised to the power 47 times 12 plus 3, which we can further write like this. 7 raised to the power 567 is equal to 7 raised to the power 12 raised to the power 47 times 7 raised to the power 3. Now 7 raised to the power 12 is congruent to 1 modulo 13. Therefore, any power of 7 raised to the power 12 is also congruent to 1 modulo 13. 7 raised to the power 567 is congruent to 7 raised to the power 3 modulo 13, which is congruent to 343 modulo 13. And in turn, 7 raised to the power 567 becomes congruent to 5 mod 13. Since 5 is a non-negative integer less than 13, 5 is the remainder when 7 to the 567 is divided by 13.